Dear students, welcome to the online class. I am Dr. S.C. Hiramat. In this video, you are going to study about the complex reactions. In that, first let us study about the reversible reaction or opposing reactions. A reaction or the reactions which take place in the opposite direction are reversible to each other. They are called the reversible reactions. Means the reactions in which reactants react to give products and products react to give the reactants simultaneously are known as reversible reactions or opposing reactions. It can be explained with the help of the diagram. That is extent of a reaction. Here this is concentration. Now suppose at this point reactants concentration. Now the concentrations of reactants goes on decreasing as the reaction proceeds. Suppose this is the concentration of products. Suppose the same reaction is started with the products, then the concentration of the products goes on decreasing in this way. Now this may be shown as the dotted line. Here this is forward reaction takes place in this direction and backward reaction takes place in this direction. At this point one equilibrium is reached. That is equilibrium is reached. After the equilibrium, reaction does not take place either this direction or in that direction. Okay, here the concentrations of the reactants goes on decreasing in this direction, whereas the concentration of the product goes on increasing in this direction and goes on decreasing in this direction. Now about the energy of activation. It can be explained with the help of the energy barrier diagram. This is reaction coordinate. Here the energy. Now suppose this is the energy level of the reactants and this is the energy level of the products. To transfer the products into reactants, they have to cross an energy barrier in this way. They have to cross. If it is the maximum energy and this is the energy of activation of forward reaction. Whereas this much is the energy of activation of backward reaction, A dash, energy of activation of backward reaction. Now this difference gives the delta E of the reaction. There is energy change of the reaction. Now, when reaction is taking place in the forward direction, its energy of activation is this much. Okay. Whereas if the same reaction is to be taken place in the backward direction, this much is the energy of activation. Energy of activation is this much. Now, energy of activation of the backward reaction is more, as we are considering in this case. The energy of activation of forward reaction is less. The total energy of activation is delta E, is this much amount of energy is given out. Now, about the kinetics of reversible reaction or opposite reaction. Now, consider a reaction. A gives B. A is one reactant, B is one product. Simultaneously, B react to give reactant A. Then the rate constant of forward reaction is 1, that is K1, and the rate constant of backward reaction is K2. Okay. Now, this is a reversible reaction. Now about concentrations. Concentration. A is the initial concentration and 0 is the initial concentration of products. Suppose this is initial concentration. Means A is the concentration of the reactants initially and 0 is the concentration of the product initially. Now, A minus X and X is formed. This is at time t. At time t. The concentration of the reactants at time t. A minus X is the concentration of A and X is the concentration of B. Then A minus Xe is the concentration of the reactant A at equilibrium and the Xe is the concentration of product Xe, that is at equilibrium. At equilibrium. This is the situation. Now, at any time t, rate of the reaction may be represented as dx by dt is equal to change in concentration of A, that is rate of reaction, forward reaction, that is equal to K1 into A minus X. Then whatever the X is formed, it gives back the reactants. Then it should be minus K2 into X. Suppose this is the condition. Means at any time t, rate of forward reaction is this much and rate of backward reaction is this much and the total rate of the reaction is dx divided by dt. Thus we may write, expand this. This is equal to K1A minus K1X minus K2X. This may be written as K1A minus K1 plus K2X. Suppose this is equation 2. Now, at equilibrium, rate is equal to dx by dt is equal to, at equilibrium, rate of forward reaction is equal to K1 into A minus Xe, whereas the rate of backward reaction is equal to K2 into Xe. Now, this can be expanded, that is K1 A minus K1 plus K2 into Xe. But at equilibrium this is equal to 0. This is equal to 0. Therefore, at equilibrium this is equal to 0 means K1 equal to K1 A equal to K1 plus K2 XE. K1 plus K2 XE. Suppose this is equation 3. From equation 2 and 3, from equation 2 and 3, just you substitute the K1A for this. You get dx divided by dt is equal to K1A equal to this much. That is K1 plus K2 into XE minus K1 plus K2, K1 plus K2 X. This is equal to, you take K1 plus K2 as common and you are going to get XE minus X. Suppose this is equation 4. On rearranging equation 4, we get dx divided by xe minus x is equal to K1 plus K2 into dt. On integration of equation 5, equation 5, let us write the equation 5 once again. That is dx divided by xe minus x is equal to K1 plus K2 into bracket dt. Then on integration, this when t is equal to 0, x equal to 0. When t equal to t, sometime t, then this x equal to x. On integration of this, you are going to get ln x e minus x, that too with negative sign, because here the x is on the negative side. Okay, then integration from 0 to x is equal to K1 plus K2 into t, ranging from 0 to t. Thus we are going to get minus ln xe minus x, minus of minus becomes a plus, ln xe is equal to K1 plus K2 into when t equal to 0, that becomes 0, then this is equal to t. Then we may write K1 plus K2 is equal to, you take this on this side, that is equal to ln xe divided by xe minus x divided by t. Suppose this is equation 6. That is K1 plus K2 is equal to 2.303 divided by t log of xe divided by xe minus x. Suppose this is equation 7. Equation 7 is the expression for rate constant of rate constant, that is sum of the rate constant of a reversible reaction, reaction shown above.